The first, welcome to the first seminar of the semester. We are happy to have Ms. Ke to be here. Ke is a senior PhD student from Central China Normal University. You heard many times called the CCNU. It's the Central China Normal University with Professor Xiaofeng Liu. He has been Xiaofeng Liu. Xiaofeng Luo, Xiaofeng, yes. She has been.
I ask a question.
And let me finish my next sentence. And Ke has been working on baryon femtoscopy with the STAR managed scan program for a few years, including proton, lambda, proton cascade, and proton omega correlation function. So this study is mainly aimed at extracting scattering parameters and possibly some bound state of baryons, for example. This scattering parameters is important for understanding hyperon-nucleon interaction and the inner structure of contact sites. That's the main big picture. So today she will discuss the recent result of baryon correlation at RHIC-STAR. Yes, Peter?
So before we start, I've been to CCNU many times, has produced many very brilliant scientists. What's a normal university?
I need to do a regular.
Not optimal. It's not optimal.
Not
I think this is a translation from French. Yes, now you understand.
Not really. I never understood it in French either.
So that produce normally main purpose is training high school teachers. But now the many normal universities want to become bigger, more expensive, and stronger. They also do basic science. CCNU is one.
It's from when it was an educational institution.
Yes, but CCNU is one of very good ones to hire. Started from. Yeah. Okay. You don't agree, Tom?
100% agree.
Yeah. I think it's from some extent better than Peking University. All right, so Ke, are you ready? If you're ready, please start, and we will listen, and we also, from time to time, there will be questions. I'll let you know. Thank you. Can you start?
Okay, thank you. I hope you can hear me and see my slide.
Yes.
So first of all, I'd like to thank the organizers for giving me this great opportunity to present our work. I'm Ke from CCNU. So today I'd like to talk about the recent results of the baryon correlations measured at the RHIC-STAR experiment. This is the outline of my talk. Firstly, I will give you an introduction about the femtoscopy, Laninsky-Lubavitch model, motivation, and also the STAR detector. Then I will show the results about the PP-PD-DD correlation and P-lambda-D-lambda correlation, as well as the P-cascade lambda-lambda-P-omega correlations. Finally, I will summarize my talk and give you an outlook. So, as we all know, that the femtoscopy is inspired by the Henry-Baryon twist interferometry used in astronomy, but the femtoscopy measured in a different smaller scale, usually in a several Fermi scale. Femtoscopy is a great tool to study the spatial and temporal extent of the emission source, and also to study the final state interactions, such as Coulomb interactions and the strong interactions. Recently, it is widely employed to study for the possible bound state and study its properties. So the basic quality to be measured in femtoscopy is called the two-particle correlation function. From model or from theory side, the correlation function can be written as the product of the source function and wave function. Here, the source function, the SR is the source function, and psi R is the wave function. The K-star represents the relative momentum between these two particles in their parastal frame. and r is the relative distance also in their pair raster frame. So what can be measured in experiment is that we can count the correlated pairs coming from the same event, then subtract the uncorrelated pairs coming from mixed event. The shape of the correlation functions can be both determined by the source functions and wave functions. Here I show you a simple example. If the measured correlation functions show an enhancement at small k star, then there's an attractive interactions in these two particles. On the contrary, if the measured correlation functions show suppression at low k star, so basically there will have a repulsive interactions in these two particle systems. In order to parameterize the measured correlation functions, we employ the Levitsky-Lubavitch approach, the LL function. In the LL function, few assumptions are made. And so for the source functions, the smoothest approximations are taken. And for the source, we only consider a static and spherical Gaussian source. For the wave functions, we only consider the S wave functions, and the effective range expansion is used. For the scattering amplitude, if we are dealing with the uncharged particles, the scattering amplitude Fc can be written as this function. If we are dealing with the charged particles, two additional terms need to be added. In the LL framework, we will have three physics parameters: the RG, which is a spherical Gaussian source, and the F0, the scattering length, and D0, the effective range. The sign of the F0 has different physics meaning. If the F0 is a positive value, then that means there's an attractive interactions in these two particles. If the measured code F0 is negative value, then the interactions can be repulsive interactions, or there will be a bound state. So one can distinguish these two cases by the relation between the F0 and D0. The motivation of my talk basically contains three parts. The first motivation will be to study the line nuclei formation mechanism. Since how the line nuclei are formed in the collisions are still under debate, whether it is formed via the coalescence procedure or directly produced from the fibre. And since the line nuclei are loosely bounded, by studying the line nuclear correlation, one can gain the insights to the many-body interactions as an indirect approach. The lower plot shows you the particle yield as a function of the collision energy. As one can see that at low energy, like 3 GeV, large amount of the line nuclei are produced, making it a great chance to study various line nuclei correlation. The second one is the role of the N and YN and YY interactions in equation of state is not clear, such as the interactions in the inner core of the neutron star are under investigation. The third one is to search for the strange baryons. Strange baryons have never been found experimentally, and from theory predictions, the possible bound state channels will be the H baryon decays to double lambda particles, and or proton and cascade particles. And the strange baryon will decay to p omega channels. Since they are strong decay, so by the traditional invariant mass method, one will suffer from huge background contaminations and making it difficult to see the signal. So in this case, momentum collision will provide a new way to explore the possible bound state. In this talk, I will cover 8 pair correlations. In the red plot, I show you a cartoon which I cataloged the pairs with the pair mass and also the strangeness sector. The S equal 0 sector, I will talk about the PP, PD, and DD pairs. And in the S equal 1 sector, I will talk about the P lambda, D lambda. In the S equal 2 sector, the P cascade lambda lambda pair will be discussed. At last, the P omega pairs with S equals 3 will be discussed. Okay, all the analyses are conducted in the STAR experiment. So this plot shows you the STAR detector. The STAR has excellent particle identification capability. It also has a large uniform acceptance and mid-rapidity range. In our analysis, we mainly use the time projection chamber TPC and time of flight TOF subdetectors to help us to identify particles. STAR usually run with the collider mode, but it can also collect the data under the fixed target setup. The right-hand plot shows you a cartoon about the fixed target setup. A gold target is put inside of the TPC, and the collision happens at one side of the TPC. The green dashed line shows you the acceptance of the collision under the fixed target setup with different collision energy. Since I will cover many results obtained at different energies in this talk, I try to summarize all the data set related in this talk. First, we will have 3GeV gogo collision data collected in 2018 with fixed target mode. The number of the good events is around 260 million data. Second is the 200 GeV gogo collisions collected at 2011, 2014, and 2016 under collider mode. The number of good events is around 2 billion. Third dataset is 200 GeV with isobar collisions collected at 2018 collider mode with around 4 billion good events. For the particle identifications, the protons and neutrons are identified by the TPC and TOF. The first plot shows you the dx versus particle momentum measured in TPC. Clearly, one can see that at low PT, the different particles are well separated. So at low PT, by only using the TPC, one can have clean particle identifications. But at high PT, different bands start to merge together, making it hard to distinguish particles. So at high PT, we add TOF, which measures the m square of particles to help the PID. And this plot shows you the m square distribution as a function of PT. As one can see that different particle bands are well separated up to high PT. The lower two plots shows you the phase-space acceptance of protons and neutrons at 3GeV gogo collisions. The boxes represents the analyzed range in the future correlation work. The purity of the protons and neutrons are higher than 95%. For the reconstructed particles, here we consider the lambda cascade and the omega particles. We reconstructed the hyperons via the following channels, and the reconstructed environmental mass distributions are shown in this right-hand plot. So the signals are fitted with the double Gaussian functions, and the backgrounds are fitted with the polynomial functions to calculate the purity. The acceptance of the reconstructed particles are shown in the middle plot, and the red boxes represents you the analyzed range. After we get the single particle information, we can perform the correlation work. We can calculate the correlation functions. So comes to the first part of the results. First, I will talk about the SE Cordero sector, which contains proton-neutron, which will contain proton-proton, proton-neutron, and neutron-neutron pairs. And these three pairs is related to the basic NN interactions and also the line nuclei formation mechanism. The first results I'm going to show is the proton-proton and anti-proton correlation functions measured at 200 GeV gogo collisions. This result has been published in Nature at 2015. The measured correlation functions are shown in the right-hand plot. From top to bottom is proton-proton, anti-proton, and the ratio between them. One can see that the ratio is close to 1, which means the correlation functions are consistent between the proton-proton and anti-proton. By fitted with the LL model, the extracted scattering lengths for antiprotons are shown as these red star points. Compared with the proton-proton interactions shown as this red circle, one can see that within the uncertainties, the F0 and D0 are consistent between these two systems. And the F0 value is around 7.4 Fermi, which is a positive value, meaning an attractive force in proton-proton and antiproton systems. By comparing the interaction parameters for proton-proton and antiproton, the results provides an quantitative variation of the CPT symmetry from a new aspect. Then the slide 18 shows you the proton-neutron correlation measured as 3GeV coefficients. The top panel shows you the proton-neutron correlation function as a function the PD correlation functions. And the lower plot shows you the DD correlation functions. This is the first measurements of PD and DD correlations in heavy collisions. And the measurements are conducted with 4 centralities. From left to right is from central to peripheral collisions. The data points are shown as these open markers. First, by looking at the data, a clear depletion is observed at RHIC-STAR. This is mainly due to the Coulomb repulsive interaction between these two particles. We use the LL functions to fit our data simultaneously, which means we assume that in different centrality, only the source size will change. The strong interaction parameter F0 and D0 will not change. And I will discuss the fitted results in the following slides. In order to study the production mechanism of light nuclei, we use the SMASH model to simulate the correlation functions. Here in SMASH model, we can consider 2 neutron formation mechanisms. The first one is neutrons are formed where the director produced with the hadronic scattering. And the corresponding simulated results are shown as these gray bands for both PD and DD correlations. By comparing with the data, the simulated CF cannot describe the data as some certain K-star. And the second production mechanism is the coalescence production. Here we use the Wigner functions to calculate the coalescence probabilities and then calculate the correlation function. The simulated results are shown as these orange color bands. And from 2 simulations, the coalescence one can provide a better description to the data. And from this, we think that the coalescence is the dominant process of neutron formation in the high energy collisions. Slide 20 discuss the source size of proton-neutron and neutron-neutron pairs extracted from LL function. The experimental data are shown as these red points, circles for PD and squares for DD. The source size are plotted as a function of centrality. We observe that there's a clear centrality dependence, which the source size is larger in central collisions and smaller in peripheral collisions. By comparing the source size of PD and DD, we found that the source size for PD is simultaneously larger than that of DD. This is due to the so-called empty dependence that the heavier particles will emit earlier. By using the same LL functions, we can fit the SMASH plus coalescence simulated correlation function, and the results are shown as these green and blue solid bands. Since the simulated correlation functions are close to the data, so the extracted source size will also closely match the data. In addition, one can directly get the root mean square RMS values from the SMASH, which is shown as these shaded color bands. One can observe that the RM's value is simultaneously larger than that of the source size extracted from LL function. And this difference can be explained as the following. In the LL fit, we assume that the source is static and spherical Gaussian source, and the expansion of the source is not taken into account. But the dynamical expansion of the source is considered in the SMASH model. For the spin average, the F0 and DD, for the spin average, the PD and DD interaction parameters, this is the first experimental extraction of those parameters in heavy-ion collisions. By comparing with proton-proton interactions, we found that the F0 of PD and DD is a negative value. This is consistent with the combination of the repulsive interaction along with the presence of the bound state in the PD and DD systems. The gray bands shows you the theory predictions for the PD interactions, and compared with our measurement, one can find that the F0 for PD is consistent within the uncertainties. This will support the feasibility of extracting the strong interaction parameters with the femtoscopy technique. The second part of my talk is S equal 1 sector, which will contain P lambda and D lambda pairs. By studying these two pairs, we can study the YN interactions, the inner structure of the compact stars, as well as the hypernuclei properties. So slide 23 shows you the P lambda correlation function as RHIC-GeV gogo collisions. Due to the lack of the statistics, the analysis is conducted only with three centralities, 0 to 10, 10 to 20, and 20 to 60%. Unlike the PD and DD correlation, we observe a clear enhancement at small k-star. Since there's no Coulomb interactions in P lambda correlation, so this enhancement is purely caused by an attractive interactions. By using the LL functions to simultaneously fit the data, we extract the spin average, the F0 and D0. And the F0 is equal to 2.32 Fermi, and the D0 is 3.5 Fermi. The slide 24 shows you the D lambda correlation functions measured in the same collision energy and collision centrality. Similar as P lambda pair, a strong enhancement as small k-star is observed. But if you look at the y-axis, the amplitude of the D lambda pairs of the D lambda correlation is much higher than that of the P lambda. That means that the attractive interactions is much higher in the D lambda pairs, or stronger in the D lambda pairs. Similarly, we use LL functions to fit the data. In the neutron lambda pair, we have two spin states, the doublet state and the quartet state. Due to the nature of the different F0 sign in these two spin states, we are able to perform a spin separate fit. And the fit results are listed here, and I will go back to this later. Let's first look at the source size extracted from P lambda and D lambda pairs. The red points are the P lambda source size, and the blue points is the D lambda source size. A clear centrality dependence is observed in both P lambda and D lambda, and the empty dependence is also here. For the strong interaction parameters extracted from P lambda and D lambda, the fitted results are summarized in the left-hand plot. First, let's focus on the P lambda case. The experimental data are shown as these red bands from dark red to light red. It represents 1 sigma to 3 sigma fitting uncertainty. It can be seen that we have a good constraint on the F0 parameters, but low sensitivity to D0 parameter. The theory predictions for P lambda pairs for two spin states are shown as these green points. Our measurements, the spin averaged one, is seated in the middle of the theory predictions. The interaction parameters for D lambda are shown as these two blue counters. The left counter is the doublet one, and the left counter is the quartet one. Also, from dark blue to light blue is the 1, 2, 3 sigma uncertainty. The F0 for doubly spin is around minus 20 Fermi. This negative value is due to the bound state hypertriton. And the F0 for quartet spin is 16 Fermi, which means in this spin state, the interaction is a pure attractive one. Since the doublet state in d lambda interaction is related to the bound state hypertriton, we are able to use the extracted F0 and D0 to calculate the binding energy of hypertriton. Here we use the best formula to calculate, and the results is shown as these red points here, and the red line is the 1 sigma uncertainty, and the yellow line is the 2 sigma uncertainty. We compared our measurements with the world data. The lower few green points shows you the B lambda of the hypertriton measured in different experiments with different method. And the light blue bands represents you the world average values. From this, we observe that our data has modest uncertainties, and it is consistent with the world data. From this result, we think that by studying the neutron lambda interactions with the femtoscopy technique, we open a new way to constrain the hypernuclei properties. Okay, the third part of the results I'm going to show is the S equal 2 and 3, which contains P cascade, lambda lambda, and the P omega pairs. The main purpose is to study the YN and YY interactions and search for the exotic states such as H baryon and the strange baryons. Let's start from the proton cascade correlations measured at 200 GeV. We conducted these measurements in isobar collisions and gogo collisions with 3 centrality. The data shown an clear enhancement at low K-star, which is due to a Coulomb attraction and the strong interaction. We simulate the proton cascade correlation with the URQMD plus the HawkQCD simulation, and the simulated results are shown at this orange bands. And this can provide, and it is found that this can provide a good description to the data. We use the LL functions to perform a simultaneously fit by considering 9 source size and a common F0 and D0. The extracted source size are shown as a function of the DN charge d eta. The different marker represents different collision systems and the centralities. In the most central collisions, the source size is the largest. By fitting the source size with a linear function, we find that it follows a common trend in different collision systems. The URQMD results shown as these pink and blue bands follow similar trend as data. The extracted P cascade interaction parameters are shown in this plot. This is the first experimental extraction of the strong interaction parameters in P cascade systems. The red point shows you a simultaneously fit to isobar and gogo data, and the lower 3 points shows you the results of individual fit to different collision systems. One can see that with the combined fit, the uncertainty of F0 is zoomed in, and the extracted F0 is around 0.69 Fermi, a positive value, which means an attractive interactions in P cascade correlations. By compared with the proton-proton interaction parameters, which is around 7.4 Fermi, this value is rather small, which means the attractive interactions is shallow in P cascade pairs. The lattice theory prediction is shown as these blue bands, and we can see that it is consistent with our measurements. For the lambda-lambda correlations, STAR has published the lambda-lambda correlation at 200 GeV with run 10 and run 11 data. The published data is shown in the left plot. Later on, a new preliminary results with high statistics data is presented. These two results are consistent within the uncertainties. In the published paper, the F0 is extracted from the analytical LL function, and the value is around -1 Fermi. From this, a repulsive interaction is concluded from the published paper. However, it is note that the feed-down corrections are not done in the published paper, and from recent work, we find that the feed-down will have a great influence on the sign of the F0 parameters, and this has to be taken care of very carefully. At the moment, the STAR is measuring lambda-lambda correlation functions with the most high statistic data, try to extract the process interaction parameters, and these results will be released at the Quark Method 2025. The last results I'm going to show is the P omega correlation function at 200 GeV gogo collisions published by STAR. The measured correlation function with two centralities are shown as in this plot. Due to the lack of the statistics, one can only compare the theory. One can only compare the data with the theory qualitatively. Let's look at the theory predictions here. The V1, which have no bound state assumptions, V2 have with shallow bound state, and V3 with deeply bound state. By compared with the data, one can see that V3 is in better agreement with the data. This gives us the hints of the possible bound state in P omega channel, but we cannot draw the conclusion with the current publications. The STAR collaboration is also measuring the peak omega correlation with high statistic data now, and the new results will be released also at the Quark Method 2025, and more interpretations about the H-type baryon and the strange-type baryon search will be discussed. Finally, comes to the summary of my talk. I hope I have convinced you that the femtoscopy measurements from the high energy collisions provides a great tool to explore the strong interactions and the evolution dynamics. So in my talk, I first showed the results of PP, PD, and DD correlations. The interactions parameters are found to be consistent between PP and anti-P pairs. And in the PD and DD correlations, we find that the coalescence is the dominant process of neutron formation in high energy collisions. And in the P lambda and the D lambda correlations, we propose a new way to explore the hypernuclear properties. The third part is the P cascade lambda and P omega correlations. In the P cascade pairs, an attractive interaction is found. But in the lambda and the P omega pairs, no conclusive evidence about the H-type baryon or the strange-type baryons can be drawn at the moment. We need high statistic data to tell us. For the outlook, as you may know, that more than 10 times data are collected from the beam energy scan 2 program, making it possible to study such as the emission source size versus the energy and the rapidity, and also to perform the study with baryon-baryon, baryon-meson, and meson-meson correlations with many different particle pairs. Here, I want to emphasize you that the excited results will be released in Quark Method 2025. We will have two related talks. The first one is the measurements of the line nuclei and the lambda correlation in 3 GeV from STAR. And the second one is the search for the strange-type baryon with baryon correlations in isobar collisions. And many nice results will also be presented soon. So stay tuned for the new results. And here, thank you for your time.
Thank you very much for a nice talk. So now we can take a few questions. Peter first.
Yeah, so there's wonderful talk, really fantastic results. A question on, I think it was slide 17, the comparing the correlations of antiprotons pairs with proton pairs. You had both right. So the middle plot, it's the red stars, and I assume the large vertical rectangle is the uncertainty on the red star, and the proton uncertainty is very much smaller. But if I look at the actual spectra on the left-hand side, the spectra they don't look all that much different. So what's really driving the uncertainty on the antiproton measurement, and can that be improved?
Okay, so if I understand correctly, you're asking why the uncertainties of this circle is smaller than the red star?
Yeah.
Because that is due to, for the proton-proton, this is the theory prediction, now the experimental measurements. So it has no uncertainties on this red circle. But the red star is from the experimental points.
So the red star is extracted from the middle spectrum on the left?
Uh-huh.
So, but isn't the top one data from proton-proton?
Mm-hmm.
Couldn't you extract the same D0 from the proton-proton data?
Yes, but in this paper, they only presented the F0 and D0 for antiprotons.
Okay.
The protons and protons still use the theory predictions.
From left to proton pairs statistics much better.
Well, I was staring at that, if I may. I'm sorry you can't see what I'm pointing at. I'm
Draw on it.
Can I draw? How do I draw?
You can draw
With this?
No, with the,
I'm drawing for you.
Okay.
It doesn't show up.
Does that?
Not yet.
Does that work? Okay, right. So it's that one and here.
Statistics wise, it's better.
Maybe. I mean, it's a little hard to tell.
Because
But,
P ratio is about 0.8.
okay.
So that's 20%.
Anyway, but the basic answer is that this point is theory, and so there's no uncertainty. So if you do the proton-proton, it might not be so different. Okay, that's my basic questions. Okay. Thank you.
Yeah, Spencer?
Yeah, thanks. Very nice talk. One of the things you covered in the very first slide was you assume a Gaussian source, and which I guess is standard, but the source probably isn't really Gaussian. How much do things change if you? How much things, particularly S0 and D0, change if you make some different assumption about the source?
Well, we didn't run this test, but I think it will change a little bit, but not that much. Sorry, we didn't run this check.
No, it doesn't change. Because
Have you tried it? Or
Yes.
did you say that?
we tried with different centralities.
It's not quite the same. I mean, that changes the size of the source, but
Not sure.
They do not change by construction. Okay, if it changes, then you cannot separate partition the source and
Yes.
the wave function of the particles.
But that's, I think, is Spencer's question.
yeah, exactly.
Yeah, at least from this test, we tested on different centrality beams, different rapidity beams. In case of proton-proton correlation, it does not change within 3 sigma count. That was the first task we did.
My question
Yes.
is sort of similar. Why should it be spherical? Seems to me you're smashing two heavy ions together.
It's not. It has a long tail.
It says spherical.
That's a model. That's a model used to extract the parameter.
Yeah, but why should SFR depend on the magnitude of R. I mean, I did HBT calculations 20 years ago, and I had a longitudinal and a transverse, and everything was different. Sizes were different, everything was different. We were doing pions, I think, but why should it be spherical when I have these?
Baryons also different. But at least from our test, can I answer for you?
Well, you're doing it already.
Can I use this? Yes. She cannot see it. This model is the Levinsky. Basically, this wave function is separate from the source. It doesn't matter what source it is.
No, it certainly does. I've done calculations, and it certainly everything was different.
If you do pions, you don't have this part, right?
No, we had that. We had a very sophisticated, probably wrong model for pions in the final state interactions, much more detailed than on the right there.
This model is simple. It's a simple model. It's like a source. You generate a pair.
Mm-hmm.
Okay.
It's not spherical.
What we want to measure is the correlation
I understand.
between these two.
So the question is, what happens if you change the source model, or if
You have a product of two functions, and you measure in C on the left, and the examples I did, the spherical were not coming out, even at lower energies, I think.
No, it's not for proton-proton correlation. It's not spherical. We know that. That's what. Can you go to proton-deuteron slide? I don't remember.
I want to see that. So they are only
No, the summary, this plot, yes. You see if you look at in the model, the source, you see either for deuteron or proton-deuteron is much larger. It's not clear.
You know, it's just one source radius, and then
It's also tested. So the green band here is for proton-deuteron, blue is for deuteron from the fit. But you also can look into the model calculation. So here, this is also green. So it's larger because of the tail. We look at the source distribution. Same for the deuteron case. It's here.
So it means that it's like highly deviated from the Gaussian.
For source size, yes. There's a tail.
Source? So it's
For source.
it's not Gaussian.
No, it's not. The question is not here. Question is, does this affect the F0, D0?
I see.
That's a question. That's my question.
That was my question.
Yeah, that's
I think
a
generally
question. We checked. Okay, we cannot experimentally. We don't know what the distribution. We checked if we fit them separate, but the difference actually extract F0, D0 because the error bar is larger. Then we ask, are they same? And all this on top of each other for these four centrality things. In case of proton correlation, we measure many more, also rapidity. In that case, F0, D0 do not
it's spherical on average, maybe.
Yes.
So maybe can I add one more?
Of course.
So just to clarify, this is actually does not mean that it's spherical. Actually, distribution look at it, it's not spherical. They have a long tail, but this is just a fit with a spherical function. That's what it is.
Yes.
And another point to add on is maybe, if you go to the next slide, that you show the PD, the slash calculation compared with the data point.
What's the previous slide?
The previous slide, maybe 90. Sorry, the 90. Yes. The colored band that match the data points. This is taken using the coordinate space distribution from SMASH model, which is not a Gaussian source. It's whatever the model gives. But fold in with the experimental fit F0, D0 that match the data. At least it's not an exclusive test, but this will show the sensitivity. And the F0 is still consistent.
Can we take a picture from her first? Sure. Yes, go ahead. You had a question?
I already kind of asked it, but I thought because the source should be kind of different from the Gaussian. And then I was wondering how actually, so fit is not really good, right? If you it's
Right.
the
Of course,
and
so
then-
there's K.
and then
Yeah, now that we know, that's why we took us some time first to
But it
make
is-
sure.
yeah, from the model, you exactly know the source, the distribution. Because this is the final point of the interactions of the hadrons.
Yes.
And then even, so just to confirm that, like, even if you use this kind of like, so F0 is not that sensitive, it doesn't change you, or is it changing if you use a different the function rather than Gaussian?
We don't know, we are not serious, so we just use the model given to us. We did not check that. But I think it shows when we change the different with different centrality beams or with different rapidity beams, the source size change.
Yeah.
But F0, the parameter within 3 sigma, they do not. Okay, Volker?
Yeah, at this PD correlation function, I mean, I thought the proton-proton correlation function starts whatever below 1, then shoots over 1, and then comes back down.
Yes.
So why don't I see this in PD? Oh, there it was, exactly, right?
This is proton.
Yeah, I understand. So that means the attraction in PD is so much weaker than in PP. Is that what you find?
There's is that called resonance state within Bohr radius? That's
What?
exactly around the 25 MeV, the peak. It's caused by the in nucleon-nucleon interaction. This is well known. For PD, it's also well known.
Okay.
At least DD is the first time we measured this.
All right. The next question, maybe I misunderstood, is in this P lambda, you look at different spin states. Is that correct?
We couldn't because it's
No.
too close. For proton lambda, they're too close.
But somewhere you had a plot for this.
That
one,
is
yeah?
for D lambda.
So how do you do this in practice?
In practice,
Maybe K.
yes,
do you-
you can express.
Yes.
There was a
Okay.
seminar here before.
Oh yeah, but it's way.
You gave a seminar before.
Okay.
Okay, could you explain this? How do we do this?
Yeah. For the P lambda case, since the F0 values for these two spin states are too close, so from experiment it's very hard to separate these two spin
Yes.
states. But for the D lambda, I think from the theory guide that the F0 sign for these two spin states are opposite. As you can see that these purple circles points are from the theory predictions, and for the doublet states they predict negative values, and for the quartet states they predict positive values. So in our fitting, first we do a full range fit, and then we find that the minimum will the best fit will in a negative and a positive range.
Okay, so you make a joint fit, right? I mean, you don't separate experimentally between the triplet and the singlet, right? I mean, you do the joint fit of the two joints, right? Okay, all right, got it.
Doublet and quartet.
All right, thank you.
Yeah, go to page 20. I just short a question.
20,
Page 20.
20,
Yeah.
this one?
So, is there any connection between this source radii and the HBT radii, or you are just the same thing? Or no?
What do you mean HBT? HBT is for mesons. These are all these
Yeah.
areas.
So you mean for the
Okay.
pion?
Yeah.
Because I use the pound to extract HBT radii.
Whatever HBT or this is measures how this pair particle communicate at the free zone.
Yes.
This, in that sense, is same.
So in first we should give a same number.
That
No.
depends on
Yeah,
your
no,
free
like
zone.
physics, yeah,
Depends on
like
your
physics
free
must
zone. Depends on your cross section.
The underlying physics must be quite different.
Yes. That depends on the cross section.
Okay, I have another page 27 maybe.
Page
Page 27. 27.
27.
Yes, you extract the binding energy of hypertriton. Can you extract the size of the hypertriton?
Yes, we have that plot.
Yes.
But for the preliminary we didn't show.
Answer is yes. It's a 14 firm.
41, okay.
Largest, yeah, it's the largest nucleus in the world.
you're larger than KDD square. 3G.
Yes.
Okay, interesting.
How do these things compare with what's known? I think.
Known is 11 for hyper China.
In terms of Baryon energy, this gray band, this blue band is basically what,
Yes.
Blue band is the world average.
yeah, from the,
World average.
And what's the, I don't understand. The plot is the size?
What's the binding energy?
I think it
No,
was,
the binding energy.
previously it was 11 for,
It's one over the binding energy.
Yes.
It's a purely quantum state.
Oh,
Peter,
just one over the binding
TVM.
energy.
Oh, it's good. It's textbook, not PBM's paper. I copied it from a quantum mechanics textbook.
So the textbook is wrong.
It's a really low binding energy.
very low.
That's what you should have learned in quantum mechanics if you went to if you went to CCNU.
All right, any other questions online? So many participants today. Xiaofeng, do you have question?
No, yeah, very nice talk. Yeah, I don't have questions. Thank you.
That was not a question. Okay, if not, we thank Ke again. Thank you very much.